Good afternoon, everybody, and those also in the audience for this week's Infosys Chandrasekhar Random Geometry Colloquium. We're very glad to have Akashdeep, who'd deliver a series of 3 talks / mini course on minimax theories for minimal hypersurfaces. Today is the first one in the series. So without much ado, thank you very much.
And so today I'll talk about I'll talk about 2 approaches for the min-max construction of minimal hypersurfaces, that is the Almgren-Pitts min-max theory and the Allen-Cahn min-max theory, and to what extent these 2 theories agree. So throughout Mn plus 1 will denote a closed Riemannian manifold. And n plus 1 will be the ambient dimension. So let us consider the space of closed hypersurfaces in M. So on this space we have the area functional. So for a hypersurface sigma inside M by area of sigma, we just mean the codimension 1 volume of sigma. And minimal hypersurfaces are precisely the critical points of this area functional. More precisely, this means the following. So given a vector field X on M, let fxt denote the flow of X. And we say that a hypersurface sigma is minimal. So sigma is minimal if and only if ddt at 0, area of fxt sigma is equal to 0 for all vector field X. So given a vector field X, we deform sigma in the direction of flow of X, and then we consider ddt of area at t is equal to 0, and we say that sigma is minimal if and only if this derivative is 0 for all vector field X. And this is precisely what it means to say that minimal hypersurfaces are the critical points of the area function. So the idea of the Almgren-Pitts min-max theory is to construct these critical points, that is the minimal hypersurfaces, using a min-max method. But before describing the Almgren-Pitts min-max theory, I will briefly describe the min-max method in the finite dimensional setup. So let N be a finite dimensional closed manifold. And if from N to R be a C2 function. So the most straightforward way to find the critical points of F is perhaps minimization, but using minimization we can only find the stable critical points of F. So a point P is called a stable critical point if the Hessian of F at P is positive semi-definite. Therefore, to find the unstable critical points, we need some other method, and that is precisely done by the min-max method. So using min-max, we can capture the unstable critical points of F. So P is called an unstable critical point if the Hessian at P is not positive semi-definite. That is, the Hessian has some negative eigenvalues. Okay, so for this min-max construction, we start by fixing a finite simplicial complex. So let X be a finite simplicial complex of dimension K. And let pi be a homotopy class of maps, of continuous maps from this parameter space X to the manifold N. And we define the min-max number of this homotopy class pi as follows. So denote it by m pi. And this is equal to sorry. Yeah, so to construct the unstable critical points of F, we need this min-max method. So for this min-max, we need to fix it. So the theorem says that if we do min-max, we will find an unstable critical point of F. But if it is a non-degenerate unstable critical point, we can do a local min-max and detect it. But here we are restricting. Here we are talking about global homotopy classes, not relative homotopy classes. So we can capture all the unstable critical points, non-degenerate unstable critical points, if we do relative homotopy min-max over relative homotopy classes. So the min-max number is defined as follows. So let us pick phi in this homotopy class, and then we take sup f phi x, small x is in capital X. So it takes sup over the image of phi, and then we take inf of this sup over all phi in this homotopy class. So this is the min-max number associated to this homotopy class, and we have the following theorem, the min-max theorem. So it says that there exists a point P in the manifold N such that P is a critical point of F. So df at P is equal to 0. F at P is equal to this min-max quantity m pi. And the Morse index of P. So Morse index of P is the number of negative eigenvalues of the Hessian at P. So the Morse index of P is less than or equal to K, where K is the dimension of this parameter space X. So X is a finite simplicial complex, and K is the dimension of this parameter space X. Yeah, so it takes sup over all little x in this parameter space, and then we take inf over all phi in this homotopy class. So this is the min-max number of pi.
For this to work, you won't need any restriction on x apart from phi.
Yeah, right. So yeah, whenever we have, so this should be a non-trivial homotopy class, meaning it should not contain constant maps, because if it contains constant map, it just becomes minimization. So for it to be interesting, this should be a non-trivial homotopy class. Yeah. But otherwise, yeah, it works. Yeah. So I'll just give an example to illustrate this theorem. So I'll draw a picture here. So let us consider. So this is a classical theorem, I think. Yeah. So whenever we have a, so this says that whenever we have a non-trivial topology of this N of this manifold N, we can find a critical point using that topology.
the fact that x to n is a non-trivial homotopy class.
Yeah, x to n is a non-trivial homotopy class. So if n has non-trivial topology, that means we'll find.
There exists fine for which.
Yeah.
So just one thing, I mean, for the trivial homotopy class,
Mhm.
you have a whole ring collection of constant maps.
Yeah.
Each of them is a minimizing ring.
So if it is just the trivial thing, then we'll get inf of f. X is in, sorry, in fp, p is in n.
That's true. But I. Oh, it's already.
So these are all the global minimums. Yeah.
Okay.
So yeah, so I'll just draw a picture to illustrate this theorem. So we consider the torus embedded in R3. And on this torus, we consider the height function. So this P is a critical point of H of index 1. So near P, the torus looks like this. And we can detect this critical point P by a min-max method. So let's say C is this curve. And let pi be the homotopy class of C. So we are thinking of C as a map from S1 to torus. Okay, so from the picture, we can say that HP is equal to sup HCT T in S1. And if we take any other curve in this homotopy class pi, let's say gamma is this curve, then there exists a point on this curve whose height is at least the height of P. So this is same as saying that so H gamma T T in S1 is greater than or equal to H of P.
So this is some kind of impersonal version of Morse theory.
Yeah, so Morse theory is the interplay between topology and critical points. So if we know the critical points, we can say something about the topology. Here we are just reverting the role. We know something about the topology of the space, and we want to say something about the critical points. Yeah, so yeah, so combining these two, we can say that HP is actually the inf of this quantity. So inf so H gamma T. T is in S1, and then we take inf over all curve gamma in pi. So this is precisely the min-max number of this homotopy class pi, and this is achieved by the height of P, and index of P is equal to 1. The Morse index of P is equal to 1, and this 1 is same as the dimension of the parameter space. So our parameter space is S1, it is one dimensional, and index of this critical point is 1. So yes.
Stable critical point is still a stable critical point in the onward domain. We are scanning by things and then maximizing over the scanning by submanifold and maximizing over the submanifold, and then minimizing over.
Yeah. So yeah, so in this example, we see that corresponding to this homotopy class, we have a critical point P. And this was the idea of Almgren. So Almgren studied the topology of this space of closed hypersurfaces in M. And his idea was to use that information of topology to construct the critical points of the area functional. And minimal hypersurfaces are precisely the critical points of the area functional. So in the Almgren-Pitts min-max theory, we work with the following spaces. Cm is the space of Cauchy-Poly sets. So I'll explain this in more detail. So informally speaking, this is the space of all regions U subset M such that perimeter of U is finite, or in other words, the boundary of U has finite area. So I'll explain this in more detail. And we also need to consider the space of this is the space of mod 2 hypercycles.
I think that you are looking at things which are either rectifiable or
E-
smooth.
Yeah, rectifiable. Yeah, I am going to say about that. The boundary of U is rectifiable and n-dimensional Hausdorff measure is finite. So yeah, I'm going to say that. So this is the space of all mod 2 hypercycles in M. And informally speaking, this is the space of all closed unoriented hypersurfaces sigma, such that sigma is the boundary of a region U, where U is a Cauchy-Poly set. So yeah, so more precisely, we have the following definition for Cauchy-Poly sets. So we say that E is in Cm if and only if E is Borel and the distributional derivative of the characteristic function of E is a vector valued radon measure. So the point is that if we have a Cauchy-Poly set, let's say E is a Cauchy-Poly set, then yeah, so this statement is a Borel set. Yeah, and taking its distributional derivative is a radon measure.
That distributed over the boundary.
Yeah.
So what we're basically saying that the boundary is a random
Is n rectifiable.
distribution.
Yeah. So this radon measure will be the Dirac measure centered around the boundary. So yeah, so if E is in Cm, we can talk about the boundary of E in a measure theoretic sense. So this will be n rectifiable. And also unit normal nu E along the boundary and pointing outside. Pointing outside E, such that we have the following equality. Yeah. So integral over E divergence X. This is the n plus one dimensional Hausdorff measure is equal to integral over boundary E inner product X comma this outward pointing unit normal Levy. This is with respect to the n-dimensional Hausdorff measure, and this holds for all vector field X. So we recall that this is Stokes' theorem.
Smooth and rectifiable case.
Yeah. So Stokes' theorem, if
So there are sort of more factors.
I'm sorry.
Yeah. And
So
so it's, but I mean, I think the point is here that your boundary is, it has Hausdorff dimension in
hmm,
and it's rectifiable. So
yeah. So then therefore we have Stokes' theorem.
it's not classical, there is some technical issues here. right?
Yeah, this is De Giorgi's work. Yeah. So this is Stokes' theorem if boundary E is C1. But here our boundary E is just n rectifiable. So the space of Cacciopoli sets is a generalization for the space of open sets with C1 boundary. So this is the definition for space of Cacciopoli sets, and this Zn m comma z mod 2, this is just the space of all boundaries of Cacciopoli sets. So we have this boundary map on the space of Cacciopoli sets to Zn. It just sends the region U to the boundary of U, and this is a 2-to-1 map because let's say this is our ambient manifold. So this is sigma, and this part of manifold is U. So suppose sigma is boundary of U, then sigma is also boundary of M minus U, because M is a closed manifold and these are the only two possibilities. So this is a 2-to-1 map. Moreover, these two spaces also have naturally defined metrics on them, so they are topological spaces. This is denoted by F. This is called the flat metric on these two spaces. So the flat metric on CM is defined as follows. So let omega 1, omega 2 be two regions. Then the flat distance is simply the volume of the symmetric difference. And we also have the flat metric on the space of hypersurfaces. So roughly speaking, it means it has the following meaning. So two hypersurfaces sigma 1 and sigma 2 are closed in the flat topology. This is very small if sigma 1 minus sigma 2 is the boundary of region U such that volume of omega is small. So for instance, we could have a sphere, and then we can have a torus, which is very close to the sphere in the flat topology. So the picture will be like this. It's like this, but then there is a small. So we can arrange so that the enclosed volume is very small. So in that case, this sphere will be close to the torus in the flat topology. So it turns out that this is the right topology to consider on the space of hypersurfaces because it has good compactness property. And okay, so with this topology, these two spaces are topological spaces, and this map is a continuous map. Moreover, we have the following theorem. So this is the theorem by Marquez and Neves. So it says that the space CM is contractible. And the boundary map, which is 2 to 1, is a double cover. So this is contractible and this is a double cover, and moreover, these are metric spaces, so these are paracompact. Therefore, Zn is homotopy equivalent to Rp infinity. So the cohomology ring of this space Zn with coefficients in Z mod 2 is the polynomial ring over Z mod 2. So here lambda is in H1 Zn Z mod 2. Yeah, so this means that this space Zn, which is a space of hypersurfaces, has rich topology, and we recall that we have the area functional defined on this space. And the idea of Almgren was to use this rich topology of this space to construct the critical points of the area functional. So just as in the finite dimensional case, we start with a finite simplicial complex. So X is a finite simplicial complex of dimension k, and phi is a homotopy class of continuous maps from X to Zn. And as before, we can consider the min-max number associated to this homotopy class. This is denoted by L pi, and this is also called the min-max width of pi. So okay, so we fix a phi in pi, then we take sup area of phi x. X is in capital X, so phi is in the homotopy class pi. That means phi is a map from X to Zn. Therefore, for each small x, phi x is a hypersurface, and we are taking the area of the hypersurface phi x. So sup area phi x, and then we take in overall pi in pi. So this is the min-max number associated to the homotopy class pi, and we have the following theorem, which follows from the combined works of Almgren, Pitts, Schoen-Simon, and then recently by Marcus Neves. And Lee. It says the following: there exists a collection sigma I is from 1 to q of disjoint closed minimal hypersurfaces and a collection of positive integers mi I is from 1 to q such that this width L pi, this min max number L pi is equal to summation a mi times area of sigma I. I is from 1 to q and summation index of sigma I is less than or equal to the dimension of the parameter space. So just like in the finite dimensional case, if we do min max over this homotopy class, we get a minimal hypersurface, which is the disjoint union of the sigma is. So the sigma is can be thought of as the different connected components of sigma. And this min max number is realized by the area of this minimal hypersurface. But in this case, we have a difference that different connected components can carry different multiplicities. So these are positive integers. So the min max number is the area of the minimal hypersurface weighted by certain multiplicities. And this is the Morse index estimate for the minimal hypersurface.
Basically, this is for a particular homotopy class.
Yeah.
And so basically, okay, so this is the case where capital X is possibility is connected.
No, so we assume the simplicial complex is connected.
Connected. No, but this is for summation mi area sigma I. They're all
So the sigma is at the path, the connected components of the minimal hypersurface we get.
so the X is being mapped so that the between these things. So actually, what you will get as a minimizer is something which connects up all these sigma, but the connections are of zero volume. Is that the picture which you have in mind? Say, for example, two spheres connected by a stick. So you're really computing only the areas of the two spheres, not the volumes. Is that right? That's right. So the thing is, the minima is happening for something that is possibly disconnected.
Yeah. So the point is that when we take limit, there can be some cancellation of mass because these are currents.
That's what it is.
Yeah. So even though the parameter space is connected, so if we
Yes. Yeah, so that's
Yeah.
what I'm asking. What exactly is the cylinder actually doing the minimization? Finally, the impasse to the limit. Presumably
Yeah.
close to the limit, you will have something connected.
Yeah. Sure.
So what is the kind of regeneration that allows you to go disconnected?
Okay. So in
Just get some information about what is going on in this minimization process.
So we have a good description of that picture when the ambient dimension is 3. So in the ambient dimension 3, we don't, before going that, there is the theorem by Mix-Simonia where we minimize over isotopic class. So when we do that, there can be some neck pinching and
Yes.
it can,
So basically,
yeah.
you can,
Yeah, so-
bubble of it,
Yeah.
the thing that becomes a stick. And
right. So that we can rigorously prove only in dimension 3. And that is also not the Almgren-Pitts min-max, that is the Schoen-Simon min-max. So instead of doing min-max on this space of cycles, that is a different kind of space. So we start with some Hilbert splitting or some kind of smooth foliation by surfaces, and then we look at all the isotopic deformation of that surface, of that family of surface, and we take min-max over all isotopic deformation. And in that setting, we can give a it has been rigorously proved that these connected components correspond to that neck pinching and what exactly happens for Mix-Simonia. Yeah.
Essentially, that's for this area of spheres, probably. Right?
Yeah.
In any homotopy class, there is a unique.
Yeah, I guess if we have an injective map from pi 1s to pi 1 of a 3 manifold, then in the isotopic class of that surface, we can find it. Yeah.
Even not just yeah. So pi 1. So for example, in particular, if pi 1 is trivial, but still the homotopy class is not reviewed. For example, an S2 being mapped.
Yeah.
So I think some proofs are minimized
In the isotopy. So in the isotopy class, I think. Yeah.
Yeah, no. I think it is in the homotopy class and proofs. So for example, there is an embedding whose multiples are given by the minimizer. So for example, suppose you take an arbitrary class at pi 2.
Yeah.
That is some generator n times
The sphere.
generator.
Okay.
So the least area for the generator is actually realized by an embedded stream.
Yeah.
That is important.
Yeah, makes money on it. Yeah.
There's something very good.
Yeah, Sachs-Uhlenbeck also had some related result. Yeah, but yeah, I guess so. But Sachs-Uhlenbeck only for surfaces. Yeah. Okay, so I'll talk more about this theorem and its proof in the second talk. So now I'll move on to the next topic, which is the Allen-Cahn min-max theory. So this is another min-max theory for the construction of closed minimal hypersurfaces.
What are the derivative numbers with given when on the Allen-Cahn?
And what we can, so in mixed Simonian, there are, I think, two types of degeneration. So the same thing happened. I mean, it does not. It says that there is a sequence of neck pinching and etc. So that we get that in the min-max setup on the three manifolds. Yeah. Yeah. Right.
No. Actually, two spheres of the two ends connected.
Yeah.
Second question, why the topology is very important? Why the topology is very important?
One for every homology class you are doing.
No, so
I was asking why this ZN.
Oh, I see. Yeah.
So you have infinitely many homology or homology.
Yeah. So that I'll talk about in next time. So since HI, the ith cohomology is non-zero for every I, what we expect that corresponding to the ith cohomology class, we do min-max and we get a minimal hypersurface, and in this way we hope to produce infinitely many minimal hypersurfaces in M. So yeah, that I'll talk about later. So the Allen-Cahn min-max theory is a PD based alternative to the Almgren-Pitts min-max theory. So in Almgren-Pitts min-max theory, we are doing min-max over this space Zn, and this space Zn does not have any manifold structure. But in the Allen-Cahn min-max theory, we do min-max over a Hilbert space. So the Hilbert space we work with is the H1M. This is the Sobolev space of all functions f in L2M such that the distributional derivative of f is also in L2. So this is a Hilbert space, and on this space we have the following energy functional. This is a smooth functional on this space. So here epsilon greater than 0 is a small parameter, and we'll be interested in the case when epsilon tends to 0. So E epsilon u is equal to integral over m epsilon by 2 mod grad u square plus 1 over epsilon w and integrated with respect to the volume measure. So here W is the double well potential. So W from R to 0 infinity is a double well potential. So the graph of W looks something like this. This is -1, this is 1. So W has precisely 3 critical points, -1, 0, and 1. And W is 0 at ±1. And ±1 are non-degenerate minima. So W double prime at ±1 is greater than 0. And 0 is a local maxima. And W is symmetric. So W minus T is equal to WT for all T. And finally, we also impose the condition that W is bounded, just to make sure that this is a well-defined functional on H1M.
Any such number.
Yeah. So a typical example of this will be WT is equal to
Expected output of the min-max.
so here we do min-max for the E epsilon functional on the space H1M. And then we produce critical points of this E epsilon. And then as epsilon tends to 0, the critical points accumulate around a minimal hypersurface. So that is the idea of this Allen-Cahn min-max.
So what is it that says that as epsilon looks, so there's a that seems to be a theorem.
Yeah, that I'm going to write down. Yeah. So just an example, WT is equal to 1 minus T square whole square near -1, 1, and then outside say -2, 2, we just modify it so that it remains bounded. Okay, so I'm going to, okay, so before I write down the theorem, so I'll just write few things that U is a critical point of U. U is a critical point of E epsilon if and only if U satisfies the following PD. Minus epsilon square Laplacian U plus W prime U is equal to 0. And this is called the Allen-Cahn equation with parameter epsilon. And if U is a critical point of E epsilon, index of U denotes the Morse index of U as a critical point. So this is precisely the index of the following bilinear form. We take the Hessian of E epsilon at U. And this is going to be finite because this is an elliptic equation. So yeah, so we have this following theorem, which precisely tells the connection between the Allen-Cahn equation and minimal hypersurfaces. So this follows from the combined works of Hutchinson, Tonegawa, Wickramasekera, and Guaraco. Okay, so it says the following: suppose we have a sequence EY from M to minus 1, 1. So M is a closed manifold, and by maximum principle, we can show that any solution of this equation will be inside minus 1, comma 1. So we have a sequence Ey from M to minus 1, comma 1, I from 1 to infinity, such that so they are solutions of the Allen-Cahn equation. So AC epsilon I Uy is equal to 0 with the parameter epsilon I converging to 0. And so E epsilon Uy plus index of Uy is finite. So we have a sequence of solutions with the parameter converging to 0, and we have uniform estimate on energy and the index. Then the theorem says the following. Then up to a subsequence, so we consider the normalized energy density. So this integrand we denote by E epsilon U. This is the energy density. So we normalize it by a constant. I'm going to describe this constant. So E epsilon I Uy times the volume measure dVg. This weakly converges, meaning convergence in the sense of radon measure, to a radon measure V, which is sum of mj times sigma j. J is from 1 to some q. So these mj's are positive integers, and this notation denotes this is the radon measure defined by or associated with the minimal hypersurface sigma j. And this 2 sigma is a constant. This is the energy of the 1D solution to the Allen-Cahn equation. So I'm going to draw a picture to illustrate what is happening in this theorem. So this theorem says that whenever we have a sequence of solutions with uniform estimate on energy and index, then after a subsequence, the energy density concentrates on a minimal hypersurface. Yeah. So whenever we can ensure the existence of such a sequence of solutions, we can say there exists a minimal, there exists a. So E epsilon I Uy is that thing. So I Uy. Oh. So after a subsequence, this will converge to a radon measure, and this radon measure is given by a collection of minimal hypersurfaces.
What is there anything slightly stronger given any? So you're saying that there exists a sequence epsilon I such and a collection sigma j.
Yeah. Yes.
Suppose you take any sequence epsilon I all going to 0. Then this guarantees that you can choose a subsequence epsilon I out of those as well.
Yeah.
So which means, okay, so though it captures everything, it's basically saying that even if you take any subsequence, it will pass to a finite subsequence.
Yeah.
Then we need not converge to
But yeah, so that's my question. But you can get different.
Yeah, depending on the subsequence. Yeah.
But the last V is the same, or what is?
So the V is the limit of these radon measures. So this will in general, no.
Is the actual.
So V is the
volume
limit.
of that. The long V.
Yeah. So V is a radon measure. It is some summation.
So what I'm asking is that, yeah, so it is true that the support of that measure depends on your subsequence.
Yeah.
But does the actual volume that you get is not that is independent?
Yeah, so that will be the main theorem which I'm going to state at the end. Yeah. So informally speaking, we have this following picture that we have uniform estimate on the energy of Ey. So let's say this is our manifold M. Now, since plus minus 1 are the global minimizers of W, if I is very large, we will see the following picture. So Ui will be close to 1 on one part of the manifold. This will be close to minus 1 on another part, and then it will make a transition from plus 1 to minus 1. And this interface will roughly look like a minimal hypersurface. So the level sets of this, the zero level set of Ui resembles a minimal hypersurface. So around these UIs make a transition from plus 1 to minus 1. So we can construct such sequence of critical points using min-max theory on Hilbert space. So I'll just state that. Okay.
Is the functional of this and your manifold is n dimension.
M has a dimension n plus 1. Yeah.
So this W will look like what you have written per minus e square whole square is just one dimension.
Yeah, so W is a map from R to 0 infinity. We have to compose with U. So this will look 1 minus U square whole square. Yeah. Okay, so this space H1M minus 0, this is an infinite dimensional punctured Hilbert space. So this is contractible. And we have a Z mod 2 action on this space. Yeah, infinite dimensional Hilbert space. Yeah. So Z mod 2 acts on this space by sending U to minus U. Therefore, H1M minus 0 equipped with this Z mod 2 action is the total space of a universal Z mod 2 principal bundle. So we can let X tilde be a finite simplicial complex with Z mod 2 action. And we define pi tilde to be the set of all H from X tilde to H1M minus 0, such that H is Z mod 2 equivariant. So by the properties of universal bundle, this is a well-defined Z mod 2 homotopic class. And also our functional E epsilon is invariant under this Z mod 2 action. So E epsilon U is equal to E epsilon minus U. Therefore, so we can consider the min-max number for the E epsilon function associated to this Z mod 2 homotopic class. So this is sup E epsilon Hx x in x tilde. And then we take inf over all h in pi tilde. So this is the min max number associated with the Z mod 2 homotopy class. And yeah, so yeah, by the min max theory on the Hilbert manifolds, there exists U epsilon for all epsilon sufficiently small such that U epsilon is a critical point of E epsilon. E epsilon U epsilon is this min max quantity L epsilon pi tilde. And index of U epsilon is less than or equal to the dimension of the parameter space X tilde. So now we have a sequence of solutions with uniformly bounded index, and it will turn out from our main theorem that this quantity is uniformly bounded. So we also have a uniform estimate on the energy. Therefore, by this theorem, up to a subsequence, so this is up to a subsequence, this normalized energy density converges to a radon measure V, which is a radon measure given by minimal hypersurfaces, and the total area of V with multiplicities will be equal to limit epsilon tending to 0, 1 over 2 sigma the energy of U epsilon, but energy of U epsilon is this min max number L epsilon pi tilde. So this is 1 over 2 sigma limit epsilon tending to 0, L epsilon pi tilde. Okay, so now going back to the Almgren-Pitts side. So in the so let us consider X, which is the quotient of X tilde by Z mod 2. So there was a Z mod 2 action on X tilde. And on the Almgren-Pitts side, we have this universal Z mod 2 bundle, the space of Cacciopoli sets over Zn. This is the boundary map. And we have this covering map X tilde to X. Okay, so corresponding to this covering map, there is a canonically defined homotopy class of maps from X to Zn. Again, this follows from the properties of the universal bundle. So this is the set of all F from X to Zn. Such that kernel of F star is image of pi star. So these maps are at the level of fundamental group. So this is a well-defined homotopy class, and F is in pi if and only if there exists a lift F tilde, so that this diagram commutes. And we recall the definition of the Almgren-Pitts width of pi. This so area of phi x n phi and phi. Okay, so I guess time is over, but I just state the main theorem and stop. Yeah. Okay. So given a double cover x tilde over x, on the Almgren-Pitts side, we have a canonically defined homotopy class pi, and we can apply the Almgren-Pitts min-max theory to this homotopy class pi and get a minimal hypersurface. Also in the Allen-Cahn side, corresponding to that double cover, we have a canonically defined Z mod 2 homotopy class, and we can apply the Allen-Cahn min-max to the homotopy class pi tilde and get a minimal hypersurface here. So now we can ask the question, to what extent these two theories agree, meaning what is the relationship between the minimal hypersurfaces obtained by the Almgren-Pitts min-max theory versus the Allen-Cahn min-max theory. So, okay, so here this limit exists only after subsequence. So, but I'll just denote it. Just write it as the Allen-Cahn width of pi tilde. Okay, so the following theorem was proved by Guaraco and Gaspar Guaraco. So they proved the following inequality between the Almgren-Pitts width and the Allen-Cahn width. They proved that the Almgren-Pitts width of pi is less than or equal to 1 over 2 sigma times lim epsilon converging to 0 L epsilon pi tilde. And then I proved that the reverse inequality also holds. So So 1 over 2 sigma lim sub epsilon tending to 0 L epsilon pi tilde is less than or equal to the Almgren-Pitts width of pi. So combining these two inequalities, we can say that, yeah, and this is equal to the Almgren-Pitts width of pi.
So you that is independent of this.
Yeah. So this says, so this is the area of the minimal hypersurface obtained by the Allen-Cahn min-max theory, and this is the area of the minimal hypersurface obtained by the Almgren-Pitts min-max theory, and this says, this equality says that those two numbers are equal. Moreover, we can say the following. If V, which is a minimal hypersurface with multiplicity, is obtained by the Allen-Cahn min-max applied to pi tilde, then V is also obtained by the Almgren-Pitts applied to pi. Okay, so it says that if V is obtained by Allen-Cahn min-max, then it is also obtained by the Almgren-Pitts min-max. So in general, the converse is not true. But so there are some examples where certain Almgren-Pitts min-max minimal hypersurfaces cannot be obtained from the Allen-Cahn equation. However, if the ambient dimension n+1 is between 3 and 7, for a generic metric, the cardinality of this set. So the set of minimal hypersurface V such that V is obtained by the Almgren-Pitts min-max theory applied to pi. This set is a singleton set for a generic metric. Therefore, in this case, the converse holds because there is only one minimal hypersurface which is produced by the Almgren-Pitts min-max theory. So I'll stop here.
Any questions? So you got this limit where I did put well as that. So my question is, when you write the any function, you use this double value. Yet, is the double value potential important to get this to, or you could have used some other thing?
No, so even the theorem I wrote down, which says the connection between the minimal hypersurface and the equation and the Allen-Cahn equation. So even for that, it is important to have a double well potential.
You tell us something about the importance of that next time, or why actually about the next talk?
I say next talk, I was planning to talk about the modes theory for the year.
So I have just one question. So, this is going to go. Does it also affect the CBD measure, error measure that you get supported on this collections of?
Yeah.
That is also like that. So that just extremize the
Yeah, no. So that theorem I wrote down that up to a subsequence we get a limit. No, I don't think that that will be unique. Yeah.
So the total volume is the
Yeah.
second thing is that this, the last thing that you said, this dimensional restriction. Just because.
Oh, so-
it is rectifiable, there are sort of very large codimensions.
Yeah, 7. So I didn't mention that. So the minimal hypersurface is obtained from both Almgren-Pitts and Allen-Cahn. They have singularity, and the singularity has at least codimension 7 in the minimal hypersurface.
And there are real examples of codimension 7 or more, or is this just a limitation of the proof?
No, so if we do the plateau problem in the Euclidean space, meaning we fix some boundary and we minimize, then there are examples of singularity. So yeah. So that's why it is not expected. Yeah. So that's why it is not expected to be able to get rid of the singularity. But an interesting open question is to say that whether every manifold admits at least one smooth minimal hypersurface. So that is not known.
That's kind of.
Thank you.